Hi everyone. In this video, we're gonna do some more work with gases, specifically looking at gas mixtures and uses of Pivnert beyond Pivnert. All right, so let's take a look at or thinking about gas mixtures. So if I have a mixture of a gas, I have a container here that contains some blue gas and it contains some of the red gas, right? Remember that the key thing about gases is that there is no interaction between molecules. There's no intermolecular forces. That's kind of the hallmark of a gas. So if there's no interaction between these gas molecules, then it really doesn't matter if there's other gas molecules in the container or not. There's just no interaction. So each gas molecule and each gas identity is going to behave completely independently, right? So it's going to behave independently, which means, right, they're in the same container, which means they have the same volume. They have the same temperature, but because they're, again, in the same container, so same volume, same temperature, but what they don't have necessarily is the same pressure. Because remember, each one of these guys is moving, they're all colliding here. The pressure is going to be proportional to the number of moles, but it's going to have a different pressure. So the pressure that is exerted by the blue molecules plus the pressure that is exerted by the red molecules is going to equal the total pressure inside the container. And so the idea here is that partial pressures or pressures are additive. We call this a partial pressure, so it's the pressure that's exerted just by the blue molecules. And pressures tend to be additive. Not tend to be, pressures are additive. And this idea that the partial pressures add total is given a special name. It's called Dalton's law of partial pressures, which basically just says that the total pressure inside a container is equal to the sum of all of the partial pressures of the gases. So it's equal to P gas 1 plus P gas 2 plus P gas 3, etc. And kind of continuing on from that way. Pressures are additive, okay, which totally makes sense. When you think about it, because they're behaving it again independently, so it makes sense that the pressures are going to add together. And again, remember that because they're in the same container, they have the same volume and they have the same temperature, which means that the partial pressure, is going to be proportional to the number of moles of the gas. Right, so the partial pressure of A is going to be proportional to the number of moles of A that are present in the container. Partial pressure of B is proportional to the number of moles of B in the container. Okay, so let's say that I have a container that has 1.2 atmospheres of oxygen, 0.5 atmospheres of nitrogen, and 0.75 atmospheres of argon. Right, so to find the total pressure, I can add them together, which is straightforward, and I'm going to assume that we can all do that. Which gas, if I'm thinking about this, which gas do I have the most of, is an interesting question to think about. So remember, they're in the same container, which means they have the same volume, the same temperature. Partial pressure is proportional to the number of moles of gas. So in this container contains mostly oxygen, with some amount of nitrogen and some amount of argon, but oxygen is going to have the largest, what we call mole fraction, because I just have the most number of moles of oxygen compared to the number of total moles in the container. Okay. All right, so let's take a look at an example problem dealing with this. So we have an apparatus that's shown below that has some gases at volumes and temperatures. And let's think about what happens when this valve is open. So if I open the valve and allow the gas to mix, what happens to the volume of the N2 gas? What happens to the partial pressure of N2? What happens to the volume of O2? What happens to the partial pressure of O2? And then how do we figure out the total pressure inside the container? Pause the video, think about it, give it a shot, and then press play when you're ready to see the solution. Okay, so in this container, this thing that I have, so I start out with 2 liters of N2 that's at a pressure of, so this is initial volume, that's initial pressure. And then this is initial volume and initial pressure of the oxygen. Okay. So if I'm thinking about the nitrogen, and I'm thinking about, I want to find out the final volume and the final pressure. Remember that gases expand to fill their container. So if the initial volume was 2 liters, and then I connected it to an additional 3 liters of bulk, that means that the final volume is going to be the initial volume plus the volume added. So this is going to be 2 liters plus 3 liters. So final volume that this gas is occupying is 5 liters. And remember that that final volume is actually the same as the final volume for O2. So they're both going to be 5 liters. If I'm looking for the final pressure, remember that PV over NT at any one set of conditions equals PV over NT at any other set of conditions, and NT are constant, so they cancel out. So final pressure is going to equal the initial volume times the initial pressure over the final volume. So that's going to equal 2 liters times 1 atmosphere over 5 liters. So the final pressure of the nitrogen is going to equal 0.4 liters, or sorry, 0.4 atmospheres, which makes sense. We're expanding it. It's going into a bigger volume. The pressure should go down. So the partial pressure of the N2 is 0.4 atmospheres. Following the same process, with the same logic, the final partial pressure of the O2 ends up being 1.2 atmospheres. Same again, PV equals PV. Solve it that way. It makes total sense. The pressure should go down because the volume went up. So the total pressure, the partial pressure of the O2 inside the container should go down. All right, so when I'm thinking about the total pressure, it's going to be equal to the partial pressure of the nitrogen plus the partial pressure of the oxygen. So that's going to equal 0.4 plus 1.2 atmospheres. So that's going to equal 1.6 atmospheres. So the total pressure inside the container, once that valve is opened, is now 1.6 atmospheres. Okay. All right, so let's try this one again. So again, let's press play or press pause. Try this one where we're looking for, we have a mixture that contains 0.765 moles of helium, 0.330 moles of neon, and 0.110 moles of argon. It's confined to a 10-liter vessel at 25. I want you to calculate the partial pressures of each gas, and then the total pressure inside the container. Press play, or press pause, sorry, give it a try, and then let me know when you're ready to hear this, and then let me know. Press play when you're ready to hear the final solution. Okay, so breaking this down, we're going to look at each of the gases separately because I need to calculate the partial pressure, and then I need P total, so it's going to be easier to calculate the partial pressure of each and then just add them together to get P total. So starting with the helium, remember that P equals nRT over B. All right, so for the helium, you're going to just do, it's 0.765 moles of helium times R, 0.08206 liters atmospheres per mole Kelvin. Remember that you can actually do, you could use the other value for R if you want. You're just going to get an answer that's in kilopascals instead of atmospheres. I don't there's no units specified here, so it could be either one. I'm going to do it in atmospheres just because I like looking in atmospheres better. So the temperature here is 25 degrees Celsius, but remember I have to convert that to Kelvin, so that becomes 298 Kelvin. Remember, Celsius plus 273 is equal to what the temperature is in Kelvin, and I'm going to divide that by the volume, which is 10.0 liters. So the pressure of the partial pressure of the helium is equal to 1.87 atmospheres. Okay, so we follow the same process as just plug and chug with Pivnert to calculate the partial pressures of the neon and the argon. So the partial pressure of the argon ends up being, 0.269 atmospheres, and the partial pressure of the neon, following the same process, ends up being 0.807 atmospheres. In all of these cases, remember, we have 3 significant figures. Because when you add the temperature, the Kelvin temperature, that becomes 3 sig figs. So then the total pressure is going to equal the pressure of the helium plus the pressure of the argon plus the pressure of the neon, which in this case, when you add all those numbers together, ends up being 2.95 atmospheres. So the total pressure inside the container is 2.95 atmospheres, and then the partial pressure of helium, argon, and neon are as followed over there. Okay, another thing about thinking about gas mixtures that we need to think about, which is the idea of collecting a gas by bubbling it through water. So if I collect a gas by bubbling it through water, or for any other liquid, it's actually a really good way to get a sample of a gas that doesn't have any air in it. But we have to think about something else. So let's say that I'm collecting a sample of carbon monoxide by collecting it over water. So I'm bubbling it through water and collecting it, and the total pressure inside the container is 756 torr at 18 degrees Celsius. Okay, cool. My question to you, and something to think about, is carbon monoxide the only thing that's in the container, the only gas that's in the container, if I'm collecting it over water or collecting it over any liquid? And the answer to that is no, it's not. Remember that even though when I think about water, water boils at 100 degrees Celsius, but there's actually some water vaporizing at any temperature. That's why a glass of water will evaporate on the counter rather than just staying there indefinitely. Even though, because it's not boiling, puddles evaporate even though they're not boiling, because some of the gas is consistently turning into things. And so we call that amount's called the vapor pressure. And so some of these are going to be escaping, some of them are going to be condensing, etc. And so we call that the vapor pressure. So basically what I have to do here is just look up the vapor pressure. So I have some amount in my container here. Here's my container. I have some amount of water. Then I have a lot more CO, but I have to account for the amount of water that's there. All right, so in this case, P total is going to equal the pressure of the CO plus the pressure of the H2O, which is the vapor pressure. So PCO is going to equal P tot minus PH2O, which is equal to 756 torr, minus the partial pressure of water, which is the vapor pressure of water at 18 degrees Celsius, which is 15.48 torr. So the pressure of the CO2 is 756 minus 15, which is 741, because I can do math. So 741 torr is the partial pressure of the CO. Right, and that's just something to keep in mind whenever you collect a gas over a liquid, that you have to account for the vapor, what's present of the vapor phase, and the vapor pressure in the container. So in thinking about PIVNERT and this idea of an ideal gas, we're thinking about gas mixtures in a container, but also we can use PIVNERT to think about and to calculate different properties of a gas, as long as that gas is behaving ideally. And one of those things is density. And remember here, the important thing here, what we're playing with here are the units. So let's think about units here. And that we don't have to memorize fancy equations, we just have to think about units. So remember that density of a gas is mass over volume. So typically for a gas, we're looking at units of grams per liter of gas. So if I'm looking at PIVNERT, right, so PIVNERT, rearranging this, can give me P over RT gets me a mole per liter. Right, so I can think about, I get paid a mole per liter, so a density in terms of moles per liter. And then I can easily convert that to grams per liter if I know the molar mass, or I know the amount of sample that I have, etc. Just like everything else in chemistry, we can think about this as a whole big game of let's make the units work. So let's look at this in action. So I'm calculating the density of NO2 at 0.97 atmospheres and 35 degrees Celsius. So in this case, all right, cool. So I'm looking for density. Remember that the units I want to end up in for density are going to be grams per liter. The thing that's missing here that you might notice is I don't know how much NO2 I have. And I don't care how much NO2 I have. All that matters here is going to be the temperature and the pressure in order for me to be able to determine the density. So let's look at how this is going to work. Right? Remember, we've got a gas and we're considering it to be ideal, so PV equals nRT. Density is in units of grams per liter, so I need something about an amount on the top and something about volume on the bottom. Easiest way for me to get there is going to be N over V, so the number of moles divided by the volume is going to equal P over RT. So in this case, this is going to equal 0.970 atmospheres over R, which is 0.8206 liters atmospheres per mole Kelvin. times the Kelvin temperature, which is 35 degrees. So 35 plus 273 is 308 Kelvin. So the Kelvins cancel, the atmospheres cancel. I'm left in 1 over liters per mole. So so that turns into moles per liter. So N over V in this case is going to be equal to 0.03837 moles of NO2 per liter. Okay, so I need to get this moles of NO2 per liter of moles of NO2 per liter to grams. How do I go from grams to moles or moles to grams? The conversion factor I need here is my molar mass, which for NO2 turns out to be 46.01 grams per mole, using the molar masses that are on the periodic table. So, all right, cool. So I have 46.01 grams of NO2 for every 1 mole of NO2. And I know that I have 0.03837 moles of NO2 per liter of volume under those conditions of temperature and pressure. So the moles of NO2 are going to cancel out. I'm going to be left in grams of NO2 per liter, which is the units that I want to end up in, and that's going to equal 1.77 grams per liter of NO2. Okay, cool, right? Just a big game. Let's make the units work. Let's think about how we can get from grams to mole, how we can get from moles to liters, etc. Okay, another thing that I can use PivNert for is to determine the molar mass of a gas. All right, so remember that the units of molar mass are going to be grams per mole, and I can do moles, right? I just need to know how much that number of moles weigh, which I have to be given in the problem. So remember that N equals PV over RT. All right, so that's going to get me the number of moles of something, and if I know the mass of that sample, I can figure out the molar mass. Okay. So thinking about this, if I'm looking for the molar mass of a gas, 2.5 grams of the gas occupies 0.875 liters at 685 to 135 degrees Celsius. Okay, so I know the mass. So the mass is going to be equal to 2.50 grams, so I don't have to worry about doing anything with that. I need to know the number of moles, because remember, if I'm looking for molar mass, the units that I want to end up in are grams per mole. I know the grams. I need to know the number of moles. So N equals PV over RT in this case, so it's 685 torr. I'm going to convert that to atmospheres, and I'm just going to do it right in the problem because I'm lazy. PV, so in this case, volume is 0.875 liters over R, 0.08206 liters atmospheres per mole Kelvin, times temperature in Kelvin, which is temperature in Celsius is 35. 35 plus 273 is 308. Through 308 Kelvin unit-wise. Torrs cancel, atmospheres cancel, liters cancel, Kelvins cancel. I'm left in 1 over moles, which ends up being moles. So the number of moles, so N ends up equaling 0.04076 moles of my gas. So to calculate the molar mass, I know that I have that sample of gas weighs 2.50 grams, and it is 200.4 this number of moles. So the molar mass of this gas ends up being 61.3 grams per mole. Again, think about the units. Think about the units that you want to be in. Think about what you know and how to get from what you know to the units that you need to be in. Okay, so to recap what we just did, right? Thinking about partial pressures. Remember that partial pressures are additive. Add them up and they should be proportional to the number of moles of gas in the container, because those gases occupy the same volume and are at the same temperature because they're in the same container, right? Remember that the units of density that we're talking about here are grams per liter, so I can use PivNert to find the liters, I can use PivNert to find the number of moles per liter, and then use the molar mass to convert that to grams per liter, or various other combinations. Just thinking about the units. Remember, all of this is really just a game of make the units work. That's it. And you need to use PivNert to be able to make the units work, right? And units of molar mass here are grams per mole. So that's it, really, just make the units work, partial pressures are additive, etc. Okay, so at this point, after this video and after you try a couple of practice problems that are listed on the on Canvas, you should be really comfortable working with PivNert, so working with PivNert in all its permutations, working with the total, partial and total pressures, and then relating the partial and total pressures to the composition of a gas mixture, and also with using PivNert to be able to find the density and the molar mass of a gas or various permutations thereof. There are practice problems that are on Canvas. We will also do some more practice in class, so don't feel like you have to do all of the practice on Canvas, etc. If you have questions, please bring your questions to the next class where we'll have a chance to go over them and to practice what we did. All right, thanks guys.